So for our first local event in the GI tract, looking at secretions, we're going to talk about saliva, secretion, its function, and its regulation. Saliva comes from a number of glands that are located in and around the mouth. You have the largest one, which is the parotid gland, that's sort of at the back of the jaw, just before the ear. And then there are two other major ones, but they are smaller in size than the parotid, and this is the submandibular or submaxillary gland and the sublingual gland. And then you have a few other minor glands in the labial, palatine, buccal, lingual, and sublingual mucosas that release saliva, but not as much as the three main ones. So the structure of salivary glands are shown here, and you can break it into two parts. You have the acinous cells that are the secretory end pieces, and there are two types. You have the serous acinous cells with zymogen granules, and these secrete salivary amylase and salivary proteins. And then the mucous acinous cells secrete glycoprotein mucus into the lumen of the ducts, and then the combination of these two secretory cells is what your saliva is when it's created and passed through the ducts. The ducts are a drainage system that goes from smaller to larger and larger. You have the intercalated ducts, which are the smallest ducts, and then they open out into striated interlobular ducts, and then the excretory interlobular ducts are the largest, and from there the salivary secretion will end up into the lumen of the GI tract. The composition of saliva is standard for GI secretion. It consists of electrolytes, proteins, and water. Water is the largest part of it by volume. And the composition of saliva depends on its secretion rate, and the reason for this is that it's a two-stage model. You get primary secretion product from the acinus, and this is very similar then in its osmolality to the plasma. And then as it's passed down through the duct system, through the striated and excretory ducts, there's a reabsorption phase where you get sodium and chloride reabsorbed into back into the blood supply, and then you get excretion of potassium and bicarbonate ion into the lumen to alter the ionic composition. And so what this results in is that generally the saliva is hypoosmotic with respect to the blood, because more sodium and chloride is removed than potassium bicarb is added, and there's no real water absorption. And because you're adding bicarbonate to it, the saliva becomes alkaline. And as I said at the start of this, the composition of your saliva is going to depend on how fast it's created, on the flow rate out of the duct. But it's always generally going to be hypotonic compared to the plasma, because regardless of how fast it's coming out of the duct, you will get some reabsorption of sodium and chloride, and as a result it ends up hypotonic. And this is sort of shown here. So we have a graph here of concentration of the mineral, and then you have the flow of saliva in mils per minute. And as you can see, that the sodium and the chloride increase as you create saliva faster and faster. The potassium decreases very slightly with increase in flow rate, and the bicarb very quickly reaches an equilibration point. The earlier increase in bicarb is just sort of how fast it can be made. And as you can see, with the highest flow rate here, the composition of the ions in the saliva is less in all cases, apart from bicarb, the than the blood. And if you were to add up the ionic content here to here, you'll find that the saliva is actually less than the blood, and so regardless of the flow rate, it's always hypertonic to the plasma. So the proteins that are produced in the saliva are shown here. You have mucin, which is a glycoprotein, and they tend to be viscous and sticky, and this is good for coating the food and allowing passage down and keeping it stuck together and ease of flow down the GI tract. There are digestive enzymes that are stored in the zymosin granules and released into the acinar lumen by exocytosis. And the two that you should be aware of is the salivary alpha amylase that breaks down carbohydrates, and then there's the lingual lipase that breaks down fats. And then together with this you have protective proteins such as the secretory immunoglobulins. IgA is one of the main ones, and then these proteins together contribute to the functions of the saliva. So looking further closer at mucus, the collective term for the secretions that contain glycoproteins is mucin, and these are characteristically viscous and sticky. They protect the mucosal surfaces from abrasion by food contents, and it lubricates the food bolus in the upper GI tract, and the alkaline pH counters the acidity of the stomach. And then mucus is produced by the various cells in the GI tract, mucus cells in the salivary glands, but also all the way down the GI tract. You have goblet cells, the Brunner's gland, the neck cells of the gastric glands, pancreatic acinar cells. These all secrete mucus, which is this aqueous colloidal solution with mucin in it. And so the functions of saliva are summarized here, and I'll just go into them as we go down. The protective functions, well, bicarbonate is added to saliva, and that creates an alkaline product, and this is important for neutralization of acid produced by both bacteria and gastric reflux. So we have a common GI complaint is gastroesophageal reflux, and saliva presents a natural mechanism to cope with this because the bicarb in it then neutralizes excessive acid influx into the esophagus. Another protective function is that it's antimicrobial. You have lysozymes that degrade bacteria, lactoferrins that will bind iron and reduce bacterial growth, and peroxidase and proline-rich proteins then further add to the antimicrobial functions of the saliva. Together with these antibacterial enzymes, you have secretory immunoglobulins that will initiate an immune response against certain antigens. And then you also have epidermal growth factor secreted with the saliva, and this allows your epithelial layer to renew or heal should there be any damage there. The function of saliva also enables mouth hygiene through these functions, neutralization of acid and the antimicrobial functions, and it also sort of lubricates your throat to help with speech, and it's important in the thirst reflex. So the digestive functions then are mainly due to the enzymes that are secreted. Alpha amylase will break down carbohydrates into smaller carbs. The lingual lipase, mentioned earlier, breaks down lipids, There are also other proteins like the R proteins that protect vitamin B12 as it goes through the GI tract. Then the mucin glycoproteins, lubrication of the food for swallowing for easy passage down the esophagus. And then also the dissolving of the substances for the taste mechanism. So soluble foodstuffs that are being chewed up get dissolved, and then these activate taste receptors so you can enjoy the food that you're eating. The regulation of salivary secretions is innervated. It's innervated by both a parasympathetic and sympathetic. The primary physiological control of the salivary gland is by the parasympathetic nervous system, and this will begin a large secretion of saliva from the different glands. The sympathetic system and hormones contribute to the regulation. Sympathetic nervous system activation tends to reduce blood flow to these areas, and as we talked about, this coupling then will reduce the amount of saliva that's produced. But there is a transient increase in salivary secretion due to sympathetic stimulation. This basically summarizes what I just said. The parasympathetic stimulation produces the high and sustained output of saliva from the salivary glands. It will also synthesize amylase and mucins. It enhances the transport activity of the ductal epithelium so that you get reabsorption of sodium and chloride at higher rates. The parasympathetic regulation will cause vasodilation and increase the blood flow, increasing the constituents that make up saliva, the access of the acinous cells to greater quantities of plasma and products to make these amylase and mucins, and it also stimulates glandular metabolism and growth. So parasympathetic stimulation is trophic to the salivary glands. Sympathetic, on the other hand, is a transient increase of secretion, but then the vasoconstriction leads to a decrease of salivation through the secretion blood flow coupling.